Our second speaker is Noor from Swiss National Supercomputing Center, and he is going to talk about Utopia, the performance portable C++ library for nonlinear algebra. So let's welcome Noor.
Thanks. Good morning, everybody. Thanks to have invited me here. So today I will talk a bit about Utopia. But before starting discussing about what Utopia is, I will let you introduce why we started working on Utopia. So, first of all, CSCS is the Swiss National Supercomputing Center. We were one of the first adopters for GPU technology in HPC, and already since 2015 we adopted GPUs with PETSc. And every scientist worldwide could access to this machine, simply asking for resources, and there will be a scientific committee that will accept. And but there was one problem when we established the PETSc, that most of the users at that time, but still now, didn't use GPUs. So there is a small benefit of using a new hardware if you are not using this hardware. And for this reason, first of all, they established a project called PASC, where the idea was to fund research workers in order to help scientists to port or improve their code in order to run on GPUs, in our case on PETSc. So, PASC project, the fields of application, these projects are many. And among these, there is also what we call PDEs, where we funded Utopia. And there are also other fields, like, for example, I've seen a poster about grid tools that's been funded through PASC. So, one example is with PDE, you probably want to solve a problem that at the end is a linear problem. You have a sparse matrix. And that means that you can or write your monolith code. There are still scientists that are writing their own monolith code, for example, in CUDA, or you use a parallel linear algebra, like PETSc or Trilinos. Nowadays, they're also hyper. And in our community, it's widely used PETSc, but PETSc has very good algorithm, also Trilinos, but unfortunately is not as mature as Trilinos in the support for GPUs. And as a past project, we start working in trying to let these communities start working on GPUs. And so what library you should use at the end? You have PETSc, but you would like to use a GPU. So here, the idea is to use Utopia. The idea of Utopia is to use both libraries. So, and our aim is to let the PETSc user use GPUs through Trilinos, exactly through Kokkos. So, who is developing Utopia? Utopia was an already existing project from USI, Università della Svizzera Italiana. The founder was Patrick, who is in the audience, and Elena and Maria. And we are supporting them, me and Andreas from CSCS. So, Utopia, it's a library written in C++11. It's open source, and if you want, you can download it. This is the link. And when we start working with the Utopia developers, had already a PETSc backend, which is still the most mature backend, and it's been designed to have self-contained backends, so it makes it easy to add new backends. And we help them in order to add these Trilinos backends. So Utopia defines EDSL, so embedded domain-specific language written in C++, and gives two freedom: the freedom to build on top of the interface new solvers, and give the freedom to add new backends. In this case, Trilinos backends. And currently, this DSL is covering linear and nonlinear algebra. Okay. So we can see Utopia as in two ways. The simple way is like a wrapper. There's a wrapping PETSc and Trilinos. So if you use Utopia, you can decide to use PETSc or Trilinos, and in the same way, you can decide to use CPUs or GPUs, or in future, other platforms like AMD, or we will see other the platforms that are supported by Kokkos. Or it's actually much more Utopia, and we can now we'll describe a bit what are the idea behind Utopia. So you have an EDSL, you can define the primitives, and it give you the possibility to create expression trees. And with these expression trees, then there is an evaluator that will map to the backend that you want to use. So in ESL, the aim of the EDSL is to separate the actual, from the idea, for example, the tensor, from the actual implementation. In our case, we have a class called tensor with two templates. One defines the backend, the other the order of the tensor here. We'll use this one. Okay. And the interaction between these tensors are defined through the Utopia primitives, and this generates an expression tree. And this expression tree is not evaluated as soon as it's been written, but is evaluated only when it's assigned to another tensor object. Then we have the expression tree. The expression tree is based on expression templates. Everything is based on template metaprogramming, advanced C++ template metaprogramming, and static polymorphism. And in the expression tree, the nodes of the tree are the expression, and can be either operators, tensor, or factories. The branches are the operation are the branches of the tree, and represent a specific operation of the nodes of the tree. And tensor and factor can be our leaves, and the tensor determines the backend, and while the factors are implicit data descriptors. And the target is to specify composition of expression without creating concrete tensor objects, and creation objects like zero, diagonal, sparse matrix. The third ingredient of Utopia is the evaluator, which is a class that is able to evaluate the expression tree, and is able to take the backend that is providing the data types and the algorithm, and map to the expression tree. Still, another important point is that always is available a row type. So in case you want to use the actual object from the backend, you still have the possibility to take it because you have this, it's exposed this row type. So one example of code is very snippet code. Here we define matrix, scalars, and an expression tree. And then here it's evaluated the expression tree. A bit more complex example is the power method iteration. You have the matrix, the vectors. Here you calculate the matrix vector product. Here the calculate the norm, and here you normalize. So, which are the benefits of Utopia? Why I should use Utopia? Well, first of all, is based on the model of write one and use everywhere, and therefore it can run on CPUs and GPUs, and you can also switch between PETSc and Trilinos, so you can try different algorithms from PETSc and from Trilinos. So comparing the same algorithm, for example, I don't know, solver GemRes with Trilinos and with PETSc, and see which is the fastest, and so on. And the benefit is performance portability, because it has near native performance thanks to Kokkos, because everything is based on Kokkos. And also it's extendable, so it's possible to create new solver based on the Utopia interface. So it's hardware and software independent. So which features are available? Of course, we haven't exposed in Utopia everything because it's almost impossible. Currently available are as provided by the native backends, direct solvers, iterative solvers, direct preconditioners, multi-grid preconditioner, and nonlinear solvers. And native in Utopia, so built on top of the backends, a possibility to mix solvers of different backends, for example, using data structure Trilinos and using solver from PETSc. Matrix-free methods that currently are not available in the Trilinos backend. Multi-level nonlinear solver, SIAM-free solvers. And be more specific about Trilinos backend, what we exposed are, of course, Kokkos, which is a common the common tools used by Trilinos packages. Of course, Tpetra, which are the data structure. Iterative solver, Belos. Precondition for Belos, if PASC2. Direct solvers, Mesos2. And multi-grid preconditioner, that's MuLU. There is also a possibility to use Nox, but it's not nowadays in the main branch. And it's only the Newton method as in nonlinear solver. So basic application. Now we will show you one example of a Utopia code compared to PETSc and Trilinos. So this is one example. On the right, you have the Utopia code. On the left is one example taken from PETSc. I underline in order to make it clear which are the logical blocks. So here you define the matrix, define the vectors. Here you read the parameters for the solvers, and here you define the solver and the preconditioner. Everything. So the one thing is in Utopia, everything is defined in the solver class and the solver method. And similarly is also with Trilinos. So next step is the code is on the Utopia side is exactly the same. Well, this is an example from Trilinos. So here you define the map. Based on the map, you create a matrix, your vectors, your linear solver, and your Belos solver. And here, for example, I put as a preconditioner if PAC. So I think you will see this code, you say, okay, but how you decide to use Trilinos or Utopia since the code is the same. Also, the input file, the parameters are very important because here you are defining a lot of things and here you are only importing one file. So in the next slide, I will show you how we design these two topics. So first of all, one thing. Here you see the matrix is called USPASC matrix and vectors are called U vectors. So at compile time, the preprocessor, we define this USPASC matrix with the keyword, and the preprocessor compile time is designed based on what you are going to decide when you compile. I want to use Trilinos or PETSc. There is also backend on BLAS, which is more for debugging region. And we'll decide to substitute USPASC matrix with Tpetra matrix, BLAS matrix, or PETSc matrix. So therefore, at the end, you will use the native data structure, and of course, this at compile time. So you cannot decide to use Tpetra matrix or PETSc matrix at runtime. In the backend is mapped to Trilinos types, so the Tpetra matrix are defined the Trilinos types. We have several types of Tpetra matrix and vector. The rules are in Tpetra traits, and the actual Tpetra object is inside Tpetra matrix, Utopia Tpetra matrix. Then another point is the input object. So what we have is input object that's reading a file. This is our data file. It's a generic data file, and this data is stored in the input object. Then is the solver of the backend that had to implement how to read the data from this generic input object and create the correct parameters for the solver. For example, for Trilinos, in the Belos solver, for example, there is this read function that will read the data inside the input object and will create a parameter list for the Belos, the Trilinos Belos solver. These are general parameters. Of course, for example, has been implemented also other, I call it advanced parameter. For example, you can use communication avoiding GMRS with Belos. And if this is implemented in the backend, we'll use. Otherwise, we'll give you an error. So how is the Utopia structure? So the Utopia structure is, okay, on top you have application. So the traits, the ingredients I told you before, the DSL, are defined in the core. Then we have the solver where we define all the interface for solvers, but the actual implementation are in backends and are mapped in the Trilinos implementation, PETSc implementation, and Plus implementation. The import and all the input-output is defined UI, and then we have also other functionalities like utils for debugging, for tracing, testing, external, where we put, for example, TinyExp that is used for evaluating the expression tree and scripting. So now we will focus on solvers on Trilinos. So solvers, we have many solvers, of course, linear, non-linear, multi-level methods, smoother for preconditioner, and Ange solver. For linear, we have one big class which is defined the generic linear solver. And every one of these are inheriting from linear. Then we have iterative solver inherits from linear, and preconditioner solver they inherits again from iterative solver. Belos has been implemented as a preconditioned solver. So the interface of Belos is this one. So we define, there are three parameters, template parameters. This, since Belos is fixed to Trilinos, these are generic in a way that you can decide which type of matrix or vector you want to use. And the interface is pretty simple. You have three functions. There are main important things: update, applied, and set preconditioner. And inside there is a smart pointer to the real implementation, so to the to the Belos object. Yeah. So in the implementation, I showed you before, there was this solve. Solve is actually inherited from the Fadel class and is calling update and apply. And applied is actually where is the Belos code. So here inside we can see the code that was hidden in the previous example. So we create the Belos linear solver, we set the solver, we read from input object the parameters, and we create the parameter list both for the linear solver, for the Belos. We create the Belos factory, we set up all the details about Belos. And then we call set preconditioner, so this function, to create, in this case, if PAC2 or mu-LU preconditioner. And then finally, we call solve. So application. Now we show you some application. As I said, this has been developed in the PASC project. So we are the main application are three, which are funded by PASC, are AVFlow, Faster, and StackBL. So AVFlow is a fluid dynamic solver, hemodynamic solver. Then Faster is the most mature code right now. We'll show you some performance details about Faster. This simulating the injection of water into cracks underground. The idea is to extract geothermal energy from the underground. And the idea is to simulate, to understand when an earthquake can happen due to the injection of water. And these are some, this is the injection of water and the activation of the faults. And then there is StackBL we are currently working on, which is a software for genodynamic simulation. So unfortunately, when we started working on Faster, we used this benchmark. This was the original code we got. We optimized the code, and this is the actually optimized code. It was a serial code, and then we ported to Utopia in order to parallelize. So simply using Utopia was parallelized, and this the performance that we got. And actually, the part is running on Utopia is the solver, and with 16 threads taking 16 seconds, and it's not anymore HPC project actually. Okay, so I will show you now a bit about the current and future work and also an ancillary project about Utopia. So now we are working on adding C binding and other interface because we have other projects that needs are not written in C++ and we would like to assess with Utopia. Another thing I'm currently working on is to refactor the Nox interface in order to use the native object of Utopia and not the Thera through Trilinos. The future work, which is the point is that Utopia is only one piece of the puzzle. You are using, okay, you invert the matrix, but often you are not using only that. And one bottleneck we found with our customers is the meshing. Often is the mesh is the bottleneck. So meshing and remeshing is the main bottleneck because you have to copy, send and receive all the time the mesh from the CPU to the GPU. So the idea now we are working is to have a general interface for meshes. Already PETSc Utopia has an interface to DM called PETSc DM, and we would like to have a general version in order to support other backends like Utopia does with the linear algebra. And we would like to support Mars. And in the future also generalize our FEM interface, which is relying on top of Utopia. Now we'll tell you a few words about what Mars is. So Mars is an ancillary project related to Utopia. It's a mesh adaptive refinement for supercomputing. It's written like Utopia in C++ using template metaprogramming that this gives compile time performance optimization, and its code is clean and reusable. The developer is still Patrick and mainly Daniel from CSCS. And it's been designed in a way that can handle n-dimensional elements. So Mars has the possibility to mesh generation 1 to 3D. The cool thing is that it has parallel adaptive mesh refinement up to 4D based on longest edge propagation path. And this keeps conforming the mesh. It has conforming mesh data structure with simplicials, hexahedra, and quads, and has also mesh quality estimators for studying the output of different mesh refinements. And everything is based on C++ 11, as I said, and on Kokkos. And this gives the possibility to have personal portability and can run on AMD, on GPUs, on OpenMP. And the mesh lives on the GPU, so you create the mesh on the GPU, so you don't need to transfer the mesh. And also the refinement is living in the GPU. So what's going on now? We are, unfortunately, it's not parallelized with MPI. We are currently working on MPI parallelization, and we are evaluating also space filling curve like pForest, so forest of tree for MPI mesh refinements. And also for one of our customers, we are working on supporting also staggered grids like PETSc. So this is a bunch of poster and publication we have done with Utopia. And for concluding, I will say that Utopia is a C++ 11 library for sparse linear and nonlinear algebra. It's MPI-based and mainly Kokkos-based. It's open source, and his design gives the possibility to use both PETSc and Trilinos. And future step, we would like also to extend this not only to use linear algebra, but also finite elements and handling meshes on GPUs. Thanks.